In this video, I want to talk about simple exponential decay, which is perhaps the simplest differential equation that you are going to encounter. And it'll basically give those of you that haven't seen too many differential equations an idea of what differential equations and dynamical systems is about. And it's simple enough, and it'll be a good review for those of you who sort of already know this. So I'm going to motivate this study of simple exponential decay by thinking of a cell. So this green thing is my cell. And suppose that this cell created some number of proteins. I'll just draw 5 of them. So these are the proteins. And let's say that the cell isn't making any more proteins. So there's no new proteins being added, but they are decaying at some rate. So perhaps there is an Pac-Man-like enzyme that is eating them up and degrading them directly. Or perhaps the cell is getting larger, so if the cell is growing, then the concentration of the protein will be decreasing even if the number of proteins is staying constant. So if we want to model the concentration of this protein within the cell, I'm going to show you exactly how we can model this decaying process. So let's say, we'll say it's a protein X, so we'll say dx dt equals negative beta x. And that's it. This is the equation that describes exponential decay. And if you look it up, it's also the same equation that would describe the rate of decay of a radioactive substance. So it's pretty straightforward when you think about it. It basically just says that x is decreasing because beta is a positive parameter. So dx dt is negative, and so the protein is decaying. And it is, the rate of its decay is proportional to the current concentration of protein X. So somebody who's seen this for the first time might say, well, why is the X in this equation? Why isn't it just dx dt equals negative beta? And if you think about it for a little bit, you'd realize that the higher the concentration of protein in the cell, the quicker the degrading enzymes, the red Pac-Man, would get to it. So if I added more proteins and suggestively put them close to the red Pac-Man, then the degrading enzyme in red would degrade the overall proteins much more quickly. So that's why dx dt is proportional to the initial, or just in general, the concentration of X. Okay, so now I am going to quickly solve this equation. This is just for some terminology. This is called an autonomous differential equation. It's autonomous because dx dt only depends on X. It's not dependent on time directly. Okay, so it's easy to solve these sort of linear autonomous differential equations. So how we're going to do it, first I'm going to divide both sides by x, so I'll have 1 over x on the right side, and we'll keep the dx over there, so dx over x equals, I'm going to multiply both sides by dt, so I'll have negative beta dt. This is just called separation of variables, so all my t variables are on my right side and x variables are on my left side. And since I've separated variables, now I can integrate both sides. So we'll integrate in red. So I'm just integrating both sides, just an indefinite integral. So the integral of 1 over x is the ln of x. So negative beta just comes out. It's a simple, it's a constant, so that just comes out. The integral of dt is just t, so negative beta t on the right side, and because these are indefinite integrals, I'm going to have a constant of integration c. And then, let's see what I want to do. So I'll clear this and just rewrite the last sentence. So we have ln of x equals negative beta t plus c. Okay, so I want to solve this equation for x, and that's pretty simple. I just exponentiate both sides. So on the left side, that gives me x, and then I have e to the negative beta t plus c. And due to the properties of exponents, this is the same thing as e to the negative beta t, e to constant c. Okay, so, and then you can notice that e to the c, this whole thing here is also a constant, because e is a constant, c is a constant, so e to the c is also a constant. So I'm going to just make a new name for that constant. I'm going to call it x0. And right here I'm just saying x of t, just to remind you that x is a variable that is dependent on t, and in this case it's the concentration of that purple protein that we had to begin with. So I'm taking this equation up here, bringing it down here, so x0 e to the negative beta t, and that's pretty much it. This gives you the value of x for all time. And you might wonder, okay, why did I call this constant x0? I called it x0 because in order to solve for the dynamics of this system. I'll just draw it again super quickly. I need to tell you how much initial protein I start out with. So if I start out with 5 proteins, I'm going to, degrade at a different rate and just a different profile than if I start out with a lot more proteins. So the more proteins I start out with, that's going to define the dynamics of the system. So I need to tell you how many proteins I begin with, and that's called the initial condition. So the initial condition is the initial amount of protein, so that's the value of x when t equals 0. So the value of x when t equals 0, well, if you just look at this, you plug in 0 for t, you get x to the 0, e to the 0, and of course e to the 0 is just 1. So that cancels out, so I chose to call this constant x 0 because it represents the initial condition, or the initial amount of protein x. Alright, and that's pretty much it. In the next video, I'll follow up on this and actually plot, and we'll look a little bit closer at what this function is really telling us about x. And as you might imagine, it's an exponential decay, so if you've seen that before, it should be pretty easy to know what to expect. Alright, so that's it for this video. Thanks.